Hello everyone. I will talk about correlators and spectral flow in 83 times H3 times T4 superstring theory. This is 83 times H3 times T4 is an exact solution for the superstring equations, and it is dual to a two-dimensional CFT located in the boundary of the 83. Next. The propagation of strings in 83 is described by the SL2R Wieso-Minowitten model that was discussed by Maldacena in the late 90s. He shown that for a complete spectrum, one must include the so-called spectrally flowed representations that are composed by the spectrally flowed primary fields. This has this unusual OPs with the affine currents that have a non-trivial pole structure. The strings in 83 can be categorized in two behaviors. In one hand, we have the short strings that are strings trapped inside the 83. And on the other hand, we have the long strings that are configurations capable of reach the conformal infinity of the 83. Semi-classically, the spectral flow parameter omega can be identified as the winding of the worldsheet around the 83 boundary. Next. In the supersymmetric theory, a complete vertex operator will be composed by different contributions. We have the ghost fields that are necessary for the quantization of the theory. We have, of course, the SL2R sector with the fermions and bosons, and the SU2 sector coming from the H3 part. As we can note that we also perform the spectral flow on SU2 in order to satisfy the Virasoro condition. As is usual, in the supersymmetric ghost system has a non-zero background charge. And then the vertex operators inserted inside a correlation function must add the total charge Q in order to the correlator to be non-trivial. This is accomplished by the picture changing procedure and leads directly to the computation of the non-primary bosonic correlator given by the last formula. Usually for unflowed fields, this kind of correlator can be computed using the Ward identities, and one can express this in terms of primary tripling functions. However, due to the non-trivial pole structure of the flowed fields, this strategy does not work directly in the spectrally flowed case. Next. In our work, we compute these correlators using this kind of operators composed by the affine currents and zeta powers that includes the insertion points, where the integral contour is chosen to encircle all the insertion points. We derive an expression for the current correlators as a linear combination of just flow primary tripling functions for arbitrary assignments of spectral flow. Schematically, we have the last equation. We reduce the problem to the computation of primary fields tripling functions. Next. In order to compare our results with the boundary CFT, it's necessary to perform a change of basis. For unflowed fields, this change of basis is given by the first formula. It's basically a sum over the spin projection M of a given H representation. For flowed fields, these have more technicalities, but it can be done similarly. These fields in the so-called X basis are interpreted as local fields in the boundary. We are interested then in the computation of tripling functions of flowed fields, where the 0 stands for the picture changing. Using the methods that we derived for the M basis, we have been capable of compute the subfamily of correlators given by the last formula. These are correlators composed by one unflowed field and two flowed ones. Next. Our results can be resumed as follows. We studied the correlators that conserve the total amount of spectral flow with arbitrary omega values as the first formula. And we've seen that our results agrees with the boundary correlators that corresponds to the so-called chiral primary operators in the boundary CPT. We also checked that our results reduce to the known cases that was derived in the literature before for some particular values of omega. Additionally, we studied process where the total amount of spectral flow is not conserved, process given schematically by the last formula. We've seen that for processes that involve only short strings, these interactions are zero up to a series identification, but give a non-trivial result for processes that involve both short and long strings. And this corresponds to one of the first examples of supersymmetrically spectral flow violation in the literature. Right now, we are working to extend our results to the complete family of correlators, taking into account the recent works of Eberhard, Kovensky, and Aniguri with new methods. And that's all.
Thank you very much, Julian. We can move on to the next speaker. Okay, our next speaker is Mritunjay Verma from University of Southampton, and that's the title. Please, Mritunjay, for yours.
So, hello everyone. I'm Mritunjay. I'm a postdoc in University of Southampton, and this talk is about deriving massive amplitudes using the momentum space representation of conformal field theories. And this work is done in collaboration with Raffaele Marotta, who is in INF in Naples, and Kostas Iskendaris, who is in Southampton. Next. So let me begin with some motivation. So at the geometric level, taking the large radius limit of radius gives us flat space. However, reproducing the flat space S matrix of a theory in this limit is a non-trivial task. But since the advent of ADS CFT during the past 20-25 years, some progress has been made to understand this limit in position and Mellin space. But momentum representation is the most natural arena for understanding the analytic properties of S matrix in flat space. Hence, it will be useful to understand and develop tools for momentum space QFT by taking the flat limit of ADS. Next. So in this work, we focus on understanding the flat limit of higher derivative theories, which involve both massive as well as massless interacting fields. And we do this directly in momentum space. So more specifically, we consider the higher derivative interacting theory involving a gauge field and a massive complex Proca field in ADS, which is described by this Lagrangian. So here FMN denotes the standard gauge field field strength. WM is the complex massive spin 1 Proca field. The alpha denotes a gyromagnetic coupling describing interaction between gauge and Proca field, and beta and gamma are the higher derivative coupling constant. And one can show that up to 3 derivative terms, this is the most general Lagrangian one can write down. Next. Now, from standard ADS CFT correspondence, we know that the gauge field AM is dual to a conserved boundary operator J mu, and the massive field WM is will be dual to some non-conserved CFT operator O mu. The mass M of the Proca field in bulk is related to conformal dimension of the boundary operator by this relation. And so L square M square is delta minus 1 delta plus 1 minus D. So from this, we see that if we want to take L going to infinity and want to keep M fixed, then we also need to send delta to infinity. So the mass of the Broca field in flat limit is defined by this formula. Next. For later purpose, we also note that the equation of motion of the Broca field imply this auxiliary condition such that the nebula of Wm, so covariant derivative of the Broca field is 0. And we shall introduce the momentum space for boundary CFT by Fourier transforming the boundary direction. And this we can do because on the boundary we have a translation invariance. We cannot do this for the bulk direction. So if Tm is any bulk quantity, we define we Fourier transform the x, but keep z as it is. Next. Now we are interested in the momentum space 3-point function involving two massive Broca field and a gauge field in flat limit. To obtain it from ADS, we start with the corresponding boundary correlator. The most general CFT 3-point function involving two non-conjugate operators, say O1, O3, and a conjugate operator J mu in momentum space can be written like this. So you have this parametrization, and these structures A, B, and C are given by this. Pi denotes a projector along the transverse direction. Next. These functions which appeared in this parametrization AI, BI, CI, they are determined using conformal word identity, and they are given in terms of this so-called triple K integral, which is nothing but the product of three modified Bessel functions. So for example, some of the functions are given in terms of these triple K integrals like this, and they involve some constants, say A1, A5, C2, etc. And these constants using ADS CFT correspondence can be fixed in terms of the ADS bulk coupling alpha, beta, gamma. Next. So to take the flat limit of 3-point function, we need to first analyze the triple K integrals in the large delta limit. And one can show that the limiting form of the triple K integral takes this form. And one can show that we also get this crucial energy conserving delta function in this limit. Next. Now for the massless gauge field, so we need to introduce the momenta and polarization in the flat limit. So for the massless gauge field, the d+1 dimensional null momentum and polarization in the flat limit can be introduced via this identification. And for the massive Broca field, the d+1 dimensional momentum vector is given in this natural manner. Next. So this auxiliary condition, which I mentioned earlier in the flat space, implies that one can parameterize the massive polarization vector in this way. So 0th component just involves epsilon1.p1. But if we impose this condition in ADS and take its flat limit, we find that epsilon1.p1 is 0. So this means that in flat limit, the polarization of massive fields take this form, so that the 0th component is vanishing. So this is like a special choice, which is consistent with flat limit. Next. So using these results, one can take the flat limit of ADS 3-point function, and the final expression for ADS 3-point function in the limit delta and L going to infinity takes this form. And this precisely matches with the 3-point function involving a gauge field and complex massive Broca field in the flat space. Next. So, to conclude, we have analyzed the flat limit of theories involving massive fields using the momentum space conformal field theories. And this gives us tools to understand properties of flat space QFT directly in momentum space from the perspective of ADS CFT. An important feature of our result is that we also include hard derivative couplings in our theory. And our analysis also gives a way to derive the gyromagnetic ratio in the flat space using ADS CFT correspondence. And this is a work in progress. So thank you.
Okay, thanks very much, Mritunjay. We can then move on to the next speaker. So on the next speaker is yes.
Go ahead.
The next speaker is Ankit Aggarwal, yes, from University of Amsterdam. Please, Ankit.
Hello, everyone. Today I'm going to talk about something that I finished recently with Glenn Barnage. It's the topic is phase transitions of photons and gravitons in a Casimir box. Can you go to the next slide? And just go to the end of the slide. Thanks. So yeah, here's the introduction and the punchline. It's widely believed that photons cannot go undergo post-Einstein condensation because the photon number is not conserved, and therefore they can be absorbed by the walls. However, this is true. However, we find a setup where they nevertheless undergo quantum phase transitions. And with appropriate boundary conditions, gravitons also show similar quantum phase transitions. Next slide. So here's the setup. It's a similar setup that is used to study the Casimir effect. There are two large parallel conducting plates, and we consider free Maxwell theory between these plates. The separation is small compared to the size of the plates. And we look at an observable that's called optical helicity. This observable measures the number of positive minus the number of negative helicity photons. And then we just compute the usual thermal partition function. Next slide. This partition function can be computed exactly, but here I'm just going to present the singular part of the partition function because that's what will be relevant for the phase transitions. At low temperatures, it's given in terms of just polylogarithms. And by low temperatures, I mean that the inverse temperature is much, much bigger than the separation between the plates. And here B is the dimensionless inverse temperature or dimensionless beta, and U is the dimensionless chemical potential. And there's a branch point at U is equal to 1. That's the maximum value, so it should be plus minus 1. That's the maximum value that you can take. Otherwise, the partition function becomes complex. And there's a branch point at this value. And if you look at the graph, you can see that for most of the, so this graph is plotting the singular part of the partition function versus the chemical potential. And you see that for the most part, it's 0. Then it suddenly jumps. And the jump occurs when B times 1 plus U is close to 1. And this signals a phase transition. Next slide, please. Yeah, so there are two phases. One is non-critical, the other is quantum critical. So the non-critical phase is when U is away from the critical value, that U is away from 1. In this phase, the partition function decays exponentially, or the singular part decays exponentially. And there's an effective massive degree of freedom. So photons effectively become massive. And then there's a quantum critical phase where U is close to the critical value. There, the singular part of partition function behaves as a power law. And this massive degree of freedom which emerged now again becomes massless. And same results hold for the gravitons with appropriate boundary conditions. If you look at the phase diagram, there are these two regions plotted, and the blue dotted line represents the crossover region. Yeah, next slide, please. Here is some outlook. So we would like to include the effect of interactions and see if this survives or if it is enhanced. Another very natural question to ask is, instead of considering this parallel plate capacitor, if you consider spherical capacitor, what happens? And it has applications to black hole physics. There are also seem to be some interesting connections to near extremal black hole physics, where extremality is also like taking the chemical potential to its maximum value. We would also like to explore it from the point of view of holography. Yeah, that's all. Thank you.
Thank you very much, Ankit. And then let's move on to the next speaker. You actually had 30 more seconds. So, yeah. Thank you. Okay, the next speaker is Aníbal Neira Gallegos from Universidad de Concepción. Aníbal, all yours.
Okay, hello. Today I'm going to talk of asymptotic symmetries in an Einstein-Scalar theory, in particular with exponential potential. This work has been done with Hernan González and Julian. Next, please. So some of you may be familiar with the no-hair theorem that says that you can't have black hole solutions with a matter field. So this was a problem for us because we wanted to include a scalar field in the theory. So the way of making it work is to include a potential that violate one of the hypotheses of this theory. In particular, the exponential potential is not bounded, so this make it work everything. Also, I'm going to tell you about how this is relevant from a holographic perspective, and how the asymptotic symmetries and the symmetry groups are related to this. Next. So here you can see some examples, because here I want to tell you that the for all spaces that are asymptotically ADS, it's very well understood the holography. So here you can see that, for example, in ADS4, they have a symmetry group of SO 3,2. And in Churchill ADS, they have a different one. But Churchill ADS4, it's contained in the asymptotically ADS4 matrix. So if we analyze these solutions asymptotically, we're going to find that they are actually have the same symmetry. Also, this symmetry group is the same as the conformal theory in 3 dimensions. Another example, another special example is in 3 dimensions, because ADS3 have a symmetry group of SO 2,2, but static BTC, like the case before, has another one. But when we study asymptotically the BTC solution, we find a bigger, infinitely more bigger group. Also, here we can see that the charge algebra, it's just 2 copies of Virasoro with a central charge, which is important if we want to analyze the microstates of the black hole. Next. So the natural question here is, can we extend these ideas to another kind of spaces? For example, asymptotically flat. Well, that's what we want to do, want to study. And the way of doing this is to consider an Einstein-Hilbert action with a 0 cosmological constant, and include the scalar field minimally coupled. And here you can see the potential, that it's also called Liouville potential. This kind of potential appears naturally in some supergravity models and in string theory. Next. So here we found already solutions, and now we want to study the asymptotic behavior of these ones. So the way of doing it is, first we need to set some falloff in the fields, and then we find a asymptotic killing vector, or asymptotic symmetry. Here we wanted to focus on a particular case that is alpha equals to 1, because it's a control case. This way we can compare with the paper, the Tornay paper, and see if we are on the right track. This in particular asymptotic killing vector is actually the same as the Tornay found. So if we choose to write the falloff, we expect to find a conserved charge that it's finite and well defined. Next. So here you can see that we already calculated, and it's finite, it's well defined, and it's integrable. And yeah, this means that the falloff condition that we choose are right, or it could be a start point to find another charges. Also, this charge is only associated with the superrotation, with the generator Y. Next. Finally, in the future, we want to generalize this to a whole range of values of alpha and see if we find something interesting. Thank you.
Okay, thanks very much, Aníbal. And then let's give a hand to all the four speakers. Thanks for